right, so to start with, we have to talk about matrix sizes. We already went over definitions of what matrices were and about rows and columns yesterday. But we need to talk about matrix sizes. Oh, I totally forgot to go over that problem. I'll help you with it. Okay, so rows and columns. Remember, rows go sideways. So this is a row. Columns go up and down. We name matrices by their size. They're named by their number of rows and their number of columns. So if I had a matrix like this, this would be a 2 by 3 matrix.
So size does matter.
Ha 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 ha. Okay, so whenever we start with addition and subtraction, in order to add and subtract, matrices have to be the same size. So if they're not the same size, you cannot add or subtract them. So adding and subtracting is very straightforward and very easy. You just take things in the exact same location and you add them together. So this is going to be, the answer is going to be 6, 2, -4, and then 4, 0, 6. So I just take items in the exact same location and add them together. So the 2 and the 4 I add, the 3 and the -1 I add, the -4 and the 0 I add, and then the 7 and the -3, -2 and 2, 5 and 1. And I put the answer in the same exact location. That's why they have to be the same size. Because if they weren't, then I would have numbers that I couldn't add to anything. So subtraction works the same way. So I take numbers in the same location and I subtract them. So I take the 3 and the 1 and I subtract them. 0 minus -4 and 2 minus -1. And then I put this one here and here just to show you one that you cannot do. Because I could add the 5 and the 2 and the 6 and the 1, but then -1 and 2 have nothing to add. So you can't do it. So that's addition and subtraction. Again, very, very straightforward. There's no tricks to it. You just get what you see. All right, you okay with that one? Questions? All right, am I good to switch? You know, man, if you spent more time writing and less time on penis jokes. Okay, so scalar multiplication. When they talk about scalar multiplication, for some reason they always use a k to represent it. All you're talking about is a single number. That's whenever they talk about a scalar. A scalar is a non-matrix number. And what you're going to do is you're going to take that times a matrix. What it's like is it's like distributing. So what I'm going to do here is I'm going to take that 2 times everything. So you really just take it and you distribute it throughout the matrix. So addition, subtraction, scalar multiplication, very simple, easy concepts, don't require really much thought at all. Yeah. Indented numbers. Can they have? Not really, because the whole point of a matrix is really to put it into a computer system, really. So you can't really put it. But then it wouldn't be infinite because you'd find it.
I know, but for every number you could add one, and then it would be infinite.
But a matrix has to be predefined, and infinity is not a number.
I thought you said indented, like if there was like a...
I said indented because I thought that's what he said. But you can't really have a matrix that's defined as infinity, because then how are you going to define all your terms?
When I say it that way, I don't mean it that way. I mean like I don't know, 100,000. You can have 100,000 rows. Like
Yeah. You can make it a matrix as big as you want to. A lot of times, because again, you use this on a computer system most of the time, you're usually limited by how much data a computer can store, because there is a limit. Trying to remember what that number is. It's a power of 2. It's like 2 to the... It's 2 to the 1,000 something. I want to say it's 2 to the 1,024, but I feel like I'm just making that up. I feel like it's a number that starts with a 6. But again, I still feel like I'm just guessing at that. I used to know what it was. Okay, so properties that go along with this. Because with addition and subtraction, actually all your mathematical properties work. It's when we get to multiplication that they don't work. But we go ahead and we just go through your properties. So properties like association, or your associative. I am not spelling that right. Something like that. Your associative rule still works. So that's the one that uses parentheses. So if I take 2 matrices and add them together with a third out here, I can move the parentheses around and add the second 2 first. And I still get the same answer. My commutative rule works. So A plus B is still the same thing as B plus A. What are all the other little tiny rules that they have? Distributing by a scalar works. So if I have a scalar here and I have A plus B, I can either add those together and then take it times the scalar, or I can take the scalar times each one of them and then add. It doesn't matter. I can also do it this way also. Although I don't know why I would go through all this. Just so you know that you can. Another thing, your zero matrix is a matrix full of zeros. However big you need it to be. And then all your zero properties work with addition and subtraction. So, you know, if I take A plus 0, I still get A. If I take scalar times the matrix 0, I still get the matrix 0 back. I think that's about all we need to talk about those. But your properties work with addition and subtraction. There's nothing special with addition and subtraction. It's multiplication where everything gets messed up. Now, one thing I want to tell you before we really get into multiplication is that there is no such thing as division. You cannot divide matrices. So as we go through these operations, we're going to talk about multiplication. We are not going to talk about division because it does not exist. It's not defined, and that's one reason. There is no definition for matrix division.
But you can like sort of do it, right? So like multiply by a fraction.
No. There's something called an inverse matrix. Inverse matrix is sort of like dividing. What you do is you turn a matrix into its inverse, and then you multiply by the inverse. That's the closest we get to division. The only problem is not every matrix has an inverse. So you can't actually divide by every matrix. Yeah?
So you can't times by like 1/2 or something?
Okay, scalars you can use any kind of scalar you want to.
Okay, so
Scalars don't matter. Yes, you can multiply by 1/2.
okay, that's right.
So when we're talking about matrix multiplication, we're talking about taking a matrix times a matrix. Whenever we take a matrix times a matrix, first of all, in order to do matrix multiplication, there are lots of rules that go along with this. These two numbers in the middle have to match on as far as the sides. So the number of columns of the first matrix has to match the number of rows of the second matrix. your answer, the size of your answer is going to be the number of rows of the first matrix times the number of columns of the second matrix. So it'll be easier to see once we actually multiply. The biggest thing is your column and rows have to match in order for this to happen. But again, I'll show you why whenever we actually do an example. When we multiply, what we do is we take a row of the first matrix times a column of the second matrix. That gives us a single answer in our answer matrix. So we take a full row times a full column and we get a single number. The way we do that is we take the first number times the first number plus second number times second number plus third number times third number, and we keep going until we've done that with all the numbers. We add them all together, and that gives us a single number. If this is like, let's say that this is the second row and first column, then this answer goes in second row, first column. So whatever row and column you use, that's where your answer goes. Okay, so let me show you this on an example. First of all, notice this has 2 rows, 2 columns. Two rows, 3 columns. So I can multiply this. The way you actually see this, note whenever we take rows times columns, I'm going to take this row times this column. The way you know that it's not possible to do is whenever you take a row times a column, you have more numbers in one of them than you do in the other one. So if you look at this one, example number 7 here is not possible. This one is not possible because if I go to multiply this row has 2 numbers. Whenever I go to multiply it times this column, how many numbers are in that column? 3. It's not possible because they don't match up. That's whenever you know that it's not possible. Now, if I write this out, this has 2 rows, 2 columns. This has 3 rows and 2 columns. Notice this number and this number don't match up. That's what I was talking about. But at the same time, if you just go and you try to multiply it, it's not going to work anyway because they don't have the same number of elements. Yeah.
What if you were to put the second matrix first?
That would work. But that's not how it's written. That's not what you're being asked to do.
Okay.
So this one is not possible. Okay, so what we do whenever we do this multiplication, We take row times column. So I take the first element in that row times the first element in this column. So I take 2 times 1. And then I add on the second elements multiplied together. Okay, that takes care of all the numbers. So I multiply and add, so that's 2 plus 4, so that's 6. Now, in my solution, so since that's the first row, first column, I put my answer in the first row, first column. Now, since I told you beforehand that you're going to end up with 2 rows, 3 columns, this is going to end up being a 2 by 3. If you don't believe me, you'll see how that happens here as we go through this. But I'm just going to go ahead and mark out all the spots. Just so you can see, first row, first row, first column, so my answer goes in that spot, first row, first column. Okay, so now after I did that multiplication, I move over a column now. So it's kind of like distributing. I'm going to take this row times each of the columns. So now I'm going to multiply it times this column. So 2 times 3 plus 1 times 0. And then I put that answer, since I used the first row, second column, I put that answer in first row, second column. Okay, so I've done first row times each of these columns. I still need to do first row times third column. So that's 2 times negative 1 plus 1 times negative 2. So that's negative 4. Okay, first row, third column, so I put the answer in first row, third column. So I'm going in order. You wouldn't even have to go in order as long as you put the answers in the correct spots. It's easier to go in order because it keeps track of it. Okay, so I took that row times each of the columns. So now I'm going to move down a row. I'm going to use this row. I'm going to take this row times each of the columns. So this row times this column. So 3 times 1 plus negative 2 times 4. So negative 5. Second row, first column. 3 times 1 is 3. Negative 2 times 4 is negative 8. Okay, now I take that row times this column. So 3 times 3 plus negative 2 times 0. So that's going to be 9. And then I do that row times the last column. So that's negative 3 plus 4, so that's 1. So even if I didn't know what size my matrix was going to be beforehand, it ends up being that size automatically. So that's how matrix multiplication works. All right, so I want to do a couple more examples of that. All right, so how about number 6? Answer 7, negative 7. That's the answer. I take row times column. Well, I have one row and one column. So I'm taking 3 times -1 plus 4 times 0 plus -2 times 2. So that equals -7. After I take that one row times that one column, I don't have any other multiplications to make, so I'm done. And if you look at the sizes, it says that my answer should be a 1 by 1, which is what I got, so I'm good. Okay, now, let's go back to what Manny said a little bit ago. Whenever he said that, well, this one here, it's no solution, but what happens if I switch it around? Then I can do it. Well, how about this one? What happens if I switch it around? Can't I? Try example 9. Because according to this is now a 3 by 1 and a 1 by 3. My middle numbers are still the same. I can do it. What size is it going to be? So my first thing is going to be -1 times 3. But I only have one element times one element, so I don't have to do any addition. So -3, -4, 2. So I took the first row times each of those columns. Now I take the second row times each of those columns. Now I take the third row times each of those columns. Now, how did this happen? In math, if I take 3 times 4, I get 12. And if I take 4 times 3, I get 12. How come if I took two of the same things and multiplied them together, how did I get two different answers? In matrix multiplication, the commutative rule does not work. And we just showed that. That's why with the other one that was no solution, Manny was correct. If we switch it around, it does work. That's because the commutative rule doesn't work. A multiplication can work in one direction, and you can switch around in the other direction, it may not work. So when we talk about properties, the commutative rule doesn't exist. AB does not equal BA. So, just realize that you cannot switch these around. Now, the rest of your rules still work. Let's see if I can spell this right this time. I think that's a little bit better. Still doesn't look right. It doesn't matter which order I do the multiplication in. It'll still come out right as long as I don't switch them around. Your distributive rule also works. I am not for sure why you would ever want to use it, but it works. The thing is, though, you have two distributive rules now. Since the commutative rule doesn't exist, those are actually two separate rules now. They're not the same. And we have one other thing. When multiplication, it's very important to be able to multiply by 1 and get the same thing back. So in matrices, it's important to be able to do that also. And we call that the identity matrix. We use an I to represent it. Whatever size it is, what it has is it has ones down the diagonal and zeros every place else. And that works like a 1. So if I would take a matrix times I get that matrix back. It doesn't matter which side I multiply the I on. So that'll be important for some of our stuff coming up. Okay, I want to do one more thing and then I promise I'm done. Okay, I want you to try number 8. If you get 9, 1, 16, 4, you're in trouble. Remember, that's what squaring means. You take something times itself. We don't have a rule saying that we distribute a square. So you actually have to do the multiplication. So that's what you should get. Nothing square about any of those numbers. So I guarantee you I'm going to give you something like that on the test. And I will take off full points if you just square each of those numbers.